We are talking about Chapter 3 today. So today's discussion is on Chapter 3. This video will show the way we will add vectors using graph paper. Some of you may be familiar with it, but some are not. So the first thing we want to do is everybody should have a piece of graph paper. You will also need a ruler that has centimeters marked on it, and you will need a protractor to measure angles with. So if you have all of your equipment together, if we wanted to add a vector, this represents a velocity, 160 meters per second at 22 degrees north of east, and then a second one at 120 meters per second at 67 degrees north of west, we would do it this way. So first thing we would do is take our piece of graph paper and using a ruler, draw a line down the middle and label it the north-south axis, and then draw a line all the way across using your ruler and label it the east-west axis. So we want to put our north, south, east, west coordinate system on the graph paper. And then we have to pick a scale. We want a scale that is big enough so that our vectors take up a reasonable amount of space, but not so big that they don't fit, or not so small that they're so teeny tiny you can't really see what you're doing. So our numbers are 120 and 160 in magnitude. And usually I start out with either, if it's a really small number, I might let 1 centimeter equal the value. If it's a really big number, I might let 10 or 100, 1 centimeter equal 10 of the value or 100 of the value. It looks to me that if I picked 10, if I said 1 centimeter equals 10 meters per second, I need to be able to draw a line 16 centimeters long, and I don't think that would fit comfortably on my graph paper. So having 1 centimeter equal 10 meters per second probably isn't going to work. So I'm going to do the next best thing, which is 1 centimeter equal 20 meters per second. So my scale is going to be 1 centimeter equal 20 meters per second. And as soon as you decide that, you need to write it on the graph. So you'll see I put it right here on the piece of graph paper in the upper right-hand corner. So we'll know the scale. That tells me that's going to be my conversion factor. So when I figure out how long the lines have to be, the vectors have to be, this is the conversion factor I'll use. Okay, now we have to convert our vectors. So vector 1 was 160 meters per second. That's going to be 160 meters per second times our conversion factor. Just like before, we write it as a fraction with a numerator and a denominator. Meters per second is what we want to cancel, so it goes in the denominator on the conversion factor. Centimeters is what we want to be left with so that we will know how long to draw the line. So we said that 1 centimeter is the same as 20 meters per second, so that's where the 1 and the 20 come from. And now you do the math. 160 times 1 is 160. Divide that by 20 and you get 8. So to represent a vector at 160 meters per second on my graph, my line has to be 8 centimeters long. For the 120 meters per second, I do it the same way. Write it down, write the conversion factor, do the math. So 120 times 1 is 120, divided by 20 is 6. So my line needs to be 6 centimeters long for the second vector. All right, so I know how long they have to be. Now I need to measure the angle so I can get them tilted the right direction. So let's look at the angle measurement. We're given 22 degrees north of east for the first vector for that 8 centimeter long one. 22 degrees north of east means start east, move north 22 degrees. So you put your protractor down on the paper. You will notice I don't line up the bottom edge of the protractor with the east-west line, but the 0 degrees. 0 degrees is right here and 180 is over there, and 90 lines up with north. You need to be really careful how you line it up or you will have your angles all wrong. We line it up and then we count up. So we're starting east. That means we start over here on the right-hand side. We move north, so that means we're going to swing up and over 22 degrees. If I just count, if this is 0, here's 10, here's 20, 22 degrees. I know my red dot is really big. Your pencil should be able to make a mark right on the 22 degree location. And now we draw in our first vector to scale. So we use a ruler. And I don't guess I showed the ruler. So you'll take the protractor, move it away, put your ruler down and measure, line up your ruler so that your origin and the 22 degree tick mark are on the ruler. So your ruler is going to connect your 22 degree tick mark. Actually, it'll extend past it. So the ruler should be on the 22 degree tick mark and on the origin. And then you, starting at the origin, want to measure a line that is 8 centimeters long. And when you do, it ought to look something like this. So I put my ruler down. I measured from the origin out. This arrow is 8 centimeters long. And this angle is 22 degrees, and it represents, now this arrow represents V1, velocity 1. And again, you won't have a big red blob there. You might have your little pencil mark. Sometimes the line we draw falls short of the pencil mark. Sometimes it goes past the pencil mark. It just depends on the line. But 22 degrees, 8 centimeters long. Now, we want to make a new north, south, east, west coordinate system at the tip of that vector. So I draw a little vertical axis, a little horizontal axis. This is our new origin because vectors are added head to tail. So the first vector is drawn from the origin. The second vector is drawn from the head of that original vector, and you just keep going. So we've got our north, south, east, west coordinate system drawn in. We know that our angle is 67 degrees north of west. So we put down our protractor. The origin lines up with our new north, south, east, west coordinate system. So the little dot in the center and the line follows north, and this east-west lines up with 0. You want to be careful about that. And now we have to go 67 degrees north of west. So start west, move north, 67 degrees. Start west, that's over here on the left side. Move north, that means swing up, 67 degrees. So if this is 0, 10, 20, 30, 40, 50, 60, this little longer line is 65. The red dot is about at 67. And again, you can do better than about because you can have a little more fine control. So you put your mark, and now we want to draw a line 8 centimeters long. We want to draw our line 6 centimeters long, isn't it? My apologies. If we scroll back, whoops. The first one was 8 centimeters long. The second one is 6 centimeters long. So if we come in, the first one was 8 centimeters long. The second one is 6 centimeters long. And it's probably not gonna extend to the little pencil mark you made. Again, yours doesn't need to be big and red. The angle 67 degrees is from this horizontal, from this brand new east-west line. It goes from there up. It is not this total inside angle. It is this little angle from the east-west, the new east-west up. And the line needs to be 6 centimeters long. And if I put my ruler down and connect my new origin with the dot, the line needs to fall on, your new vector needs to fall on that line. So the resultant, if we had a third vector, we'd do the, keep continuing, we'd put another north-south coordinates, north, south, east, west coordinate system at the tip. We'd measure our angles, we draw our vector. When you've got all your vectors drawn in, we only had 2. The resultant starts at the origin, so down here where the axes meet each other, and goes to the point of the last vector you drew. So you lay down your ruler, connect the origin with the tip of the last arrow, and we're going to draw it in as a dashed line. I usually show my individual vectors as solid lines, and my resultant, you'll notice I labeled it R. You could say V total if you wanted to, but the resultant I draw in as a dashed line just to remind myself that that's the resultant. So how long is it? You take your ruler and you measure. You go from the origin to its little tip, and when I did, I measured it to be 10 centimeters long. If I want to convert that to meters per second, I write down that R is equal to 10 centimeters. And now you'll notice my conversion factor looks different than before because it's centimeters we want to get rid of. Centimeters go in the denominator. We want to be left with meters per second. They're up in the numerator. So now I have 10 times 20 to give you 200. Divided by 1 is just 200. And the units are meters per second. So this vector, this resultant, is 200 meters per second. We need the angle. What angle? We need to go from east, so from this horizontal line, all the way up to the dashed line we just drew. So from east, all the way up to the dashed line, this whole angle. And we'll use a protractor to do that. So you put the protractor down. You will see if we count up. So here's 10 and 20 and 30 and 40 and 50, and I am right on the 60-degree mark. I might be at 61 degrees. It's a little hard for me to tell from this version. When you have it on your paper, it's easier to read. And it will be north of east because we started east, moved north 60 degrees. So the resultant, well, I guess I measured at 61 degrees, which is fine. So the resultant is 200 meters per second at 61 degrees north of east. If you don't get something similar to this, you need to see me for help. I can usually figure out what you did wrong, or you can certainly re-watch the video. Boy, I can't say that twice in a row. Okay, we're going to stop with this, and then in the second video, we'll look at how to do this using trig.